Well, hello scholars. Today we're going to take a look at the unit circle, which is more of a generalization of the trig functions and the rotation that we were looking at before. And so we're going to start off with just a basic definition. And the basic definition of a unit circle is going to be a circle that has a rotation. If I can get my highlighter on here, it has a rotation and it has a radius of 1. And so you can see that if this is true, so if this is the radius of our circle, notice that it's also, as we rotate and we form a right triangle, that it's going to give us a hypotenuse of that right triangle as being 1, which actually simplifies things a little bit when we start to look at the ratios. Because remember that if we look at this distance right here, that's really the distance of the x-coordinate. If we look at this distance right here, this is the y-coordinate. And so in the angle, when we're thinking about that perspective, then the sine is really just going to be the y-coordinate divided by the hypotenuse, which is 1, which simplifies really just to then the sine is always the y-coordinate. And then the cosine is going to be the x-coordinate divided by the hypotenuse, because that's adjacent, and that really ends up being the x. So what we end up being able to do is saying that the cosine is really away on the unit circle. The cosine is the x-coordinate and the sine is the y-coordinate. And a lot of times people will try to remember these as we go around the unit circle, just because these are alphabetical, cosine and sine, C and S, just like x and y. And so if you want to know what the sine or the cosine is of a certain location on the unit circle, look at the x-coordinate. Now the tangent is the again opposite over adjacent. So when we look at the tangent ratio, you're just going to take the y-coordinate divided by the x-coordinate. Now when we take a look at these values here, there are a few special angles that we're going to pay attention to, and obviously we're going to see that values like 0, 90, 180, 270, and 360 sort of stand out because those locations here are on either the x-axis or the y-axis. And those are going to be unique because the radius of that is extended all the way out. And so one of the values is going to be, one of the coordinates is going to be 0. So we call this quadrantial angles. And they don't fall in a particular quadrant because they're on the axis. So that's going to be one to pay attention to, and it's going to have some unique characteristics when we look at their values. The ones that we're going to look specifically at are 30, 45, and 60. And these are going to be the angles that are sort of in each quadrant. And we're going to start with the ones in quadrant 1, and then we're going to rotate around. So what you're going to notice is that the reason why 30, 45, and 60 are selected is because those actually end up corresponding to those special right triangle relationships that we talked about earlier. And so if we look at this particular value here, and we look at these reference triangles, let's talk about what that would look like. So let's say this is the 30-degree angle right here, and so it's been rotated 30 degrees. Here's the location that we're looking for, and we're looking for the x-coordinate and the y-coordinate. Now anytime that we do that, remember we're just going to draw this reference triangle. And so remember that we're going to have our x-coordinate here and our y-coordinate here, and we know that this is a radius of 1. Well, remember the 30, 60, 90, the special right triangle says that the 30-degree angle, the side across from the 30-degree angle, is actually half the size. So what we know then is that this y-coordinate is going to be 1/2, right? Because this triangle right here is 1/2. So let me replace this with 1/2. And then if you recall, the side across from the 60-degree angle is the square root of 3 multiplied by the shortest side. So in this case, instead of writing the square root of 3 times 1/2, we're going to write it as the square root of 3 over 2. So that's going to be the x-coordinate. And notice that we'll keep these as exact values, and this all happens because the radius is 1. So let's look at the other triangle here, which is the 45-degree angle rotated. Now what's unique about this one, if you recall, is that this is the only isosceles right triangle. And if we have a radius of 1 here, remember that in a 45-degree triangle, the two sides are the same, and the hypotenuse is really just those sides multiplied by the square root of 2. So if we take this and divide it by the square, 1 divided by the square root of 2, and rationalize it, both of these sides become the square root of 2 over 2. And so then this coordinate up here is going to be the square root of 2 over 2. Now this is approximately like 0.7, just so that you have a reference of kind of how tall it is or how far it is out with that. The third reference triangle we're going to look at is the 60-degree rotation. And again, if we drop this down and we make a right triangle out of it, and this is 60 degrees, notice that this is really just the 30, 60, 90, and it's flipped here. So the 30-degree angle is actually up towards the top here. And again, if this radius is 1, because this is the unit circle, then notice that these two values have just sort of switched places. And so now it's only 1/2 for the x-coordinate, so it's only 1/2 out from the origin horizontally, and then it's vertically the square root of 3 over 2. So those are the three basic reference triangles that we're going to use, and combine those with the ones on the axis, and we can actually find quite a few locations all the way around the unit circle. And that's going to be very helpful in finding when we start to graph the relationship between angles and either sine, cosine, or tangent. It's going to be helpful to have these kind of reference angles to kind of have an idea of what those look like. So if we jump back to the page in our notes here, we're just going to go through and write down each of those and talk about what those values look like. So I'm going to start out by writing what the coordinate is. So at 0 degrees, and you can kind of see the picture up here, but at 0 degrees, this is going to be the coordinate 1, 0. Because again, the radius is 1 and there's no height. So we have 1, 0. So the sine is really the y-coordinate. So we would say the sine of 0 degrees is 0. The cosine of 0 degrees is 1. And the tangent of 0 degrees is y over x. So that's 0 over 1, which is really just 0. Now, for 30 degrees, from our reference triangle, we remember that coordinate is the square root of 3 over 2 and 1/2. We found that on the triangle. And so then the sine of 30 degrees is going to be 1/2. The cosine of 30 degrees is going to be the square root of 3 over 2. And then the tangent is actually going to be 1/2 divided by the square root of 3 over 2. Now since both of these are divided by 2, this is really just 1 over the square root of 3, which we would rationalize the denominator, and the tangent of 30 degrees then is the square root of 3 over 3. If we look at 45 degrees, remember that this is the same x and y coordinate, so square root of 2 over 2. And so the sine, of course, of 45 degrees is going to be the square root of 2 over 2. The cosine, also the square root of 2 over 2. And the tangent is going to be the square root of 2 over 2 divided by the square root of 2 over 2, which is really just 1. So the tangent of 45 degrees, that ratio is always equal to 1. If we look at 60 degrees, remember that this is just 30 degrees, and the coordinates are reversed. So this is 1/2 in the square root of 3 over 2, which means that the sine of 60 degrees is the square root of 3 over 2. And the cosine of 60 degrees is 1/2. And the tangent is going to be the square root of 3 over 2 divided by 1/2, which is really just the square root of 3. Now when we get to 90 degrees, remember that this is on the axis, so this is actually 0, 1. And if we look at 0, 1, that would mean that our sine of 90 degrees is 1, the cosine of 90 degrees is 0, and the tangent is 1 divided by 0. And you really can't divide by 0 here. That is a value that is undefined. And so we remember that when we graph things like that, undefined, just like with rational functions, we're going to see that that's going to be an asymptote. If you go all the way around the unit circle to 180 degrees, that's just on the other side. Now this is going to be the coordinate -1, 0, which means that the sine of 180 degrees is going to be 0. The cosine is going to be -1, so notice that the cosine is negative. And then the tangent is going to be 0 over -1, which is really just 0. And 270, which is down at the bottom of the unit circle, that's going to be 0, -1. Okay. And again, this is going to be the special angle here, so this is going to be the sine of -270, or I'm sorry, but sine of 270 is going to be -1. Cosine is going to be 0, which means that the tangent is going to be undefined. Okay. Now, if you look at the next page is actually going to be have actually 2 pages. Is actually going to have a unit circle where we can write in all of the ordered pairs. And the thing that we're going to have to look for is 1. As you rotate a little bit further around, you're going to be able to see that we're going to be looking for the reference angles for anything larger than 90 degrees. We're going to be looking for those because that's going to tell us the triangle we're going to look at. And then we're going to adjust our coordinates based off of which quadrant it's in, because some are going to be positive and some are going to be negative when we're looking at those ratios. So let's take a look at how we come across those. Okay. So to come up with the quadrants, what we're going to do is we're just going to take a look at where things are positive and where things are negative. And so in the first quadrant, obviously both the x and y are positive. And that means that actually when it comes to which trig functions we're going to have, all of them are going to be positive. So sine, cosine, and tangent, and then all their inverses as well. Now, if you go to the quadrant 2, notice that the x coordinate, so here's quadrant 2. This is, let's go back and label this quadrant 1. So since the cosine is negative and the sine is positive, the tangent would also be negative. So when we're looking at the ones that are all positive, only the sine is going to be positive. So the y coordinate is the only thing that's positive. Now if we go down to quadrant 3, if you recall, this is where both the x and the y are both negative coordinates, which means that both sine and cosine are going to be negative. But it turns out that when you divide to find the tangent ratio and you take a negative divided by a negative, that ends up being positive. So the tangent is the only trig function, and cotangent, obviously its inverse, are going to be the only positive function there. And in quadrant 4, notice that the x coordinate is positive and the y coordinate is negative. So that means that, again, only the cosine is going to be positive here, because the cosine is the same as the x coordinate on the unit circle. And so then we have an interesting way to find all of these. Those of you that like acronyms. If you think of the phrase all students take calculus and you go around the quadrants, this will tell you which trig functions are positive, all of them, sine, tangent, cosine, as you move around this one. So all students take calculus. So that will help you perhaps remember which trig functions are positive as you go around the unit circle. Okay, so the next part I'm going to just take a look at the unit circle itself. We're going to fill in some of those, and that's going to be part 2.